The internal combustion engine converts chemical energy into mechanical energy with the byproduct of heat. Controlling this heat is the job of the cooling system. We need heat in the engine to achieve thermal efficiency. The correct amount allows for effective combustion, while too little or too much will cause engine damage, high emissions and poor fuel economy. The heat energy in an internal combustion engine is created from the combustion of oxygen and fuel. Regardless of the fuel type, high combustion temperatures need to be controlled. Excess heat energy must be removed from the combustion chamber. There are three types of heat transfer principles used in an automotive engine: conduction, convection and radiation. Conduction refers to heat transfer through a solid. We can observe this in the combustion chamber. Heat from combustion of the air and fuel mix is absorbed by the piston crown. The heat then transfers to the piston rings and cylinder wall. In an air-cooled engine, the heat transfers to the cooling fins. Remember that heat always travels to a colder object. The principle of convection relies on heat transfer through a liquid or gas. When heating a liquid in a container, the heat will transfer through the liquid, rising to the highest point. This pushes colder liquid to the heat source. Heat radiation is easily seen at the cooling fins of an air-cooled engine. As the heat from combustion travels through the fins, it transfers to the passing airstream, using the principle of radiation. Air may still be used as a cooling medium, although in the modern vehicle, liquid is much more common. Air-cooled engines require cooling fins on the outer cylinder. These distribute the internally generated heat over a much wider area. Airflow over these fins removes the heat energy. Some OEMs may use a ducted fan to circulate air. In a rear-engine vehicle, this is very important, as the engine is enclosed and does not sit in the main airstream. Liquid-cooled systems are much more efficient at removing heat energy from the engine components. Heat transfers from the cylinder bore to cooling jackets, which are cast into the cylinder head and block and contain the liquid cooling medium. The heat will transfer through the medium, travelling to cooler parts of the system, but manufacturers use pumps to efficiently circulate the liquid. The now hot liquid exits the top of the engine and is pumped into a radiator tank. The radiator is placed directly into the airstream, where it is exposed to a moving air supply. As the liquid is pushed through the radiator, heat energy is given off to the passing airstream through radiation. The now cool liquid is drawn into the pump and pushed back into the cooling jackets, and the process starts again. Water was initially used for cooling an internal combustion engine, but due to its high freezing point at 0 degrees Celsius and low boiling point of 100 degrees Celsius, engine mechanical tolerances demanded the need for wider operating temperatures. Replacing water with a manufactured product is one way to achieve this. Modern vehicles use purpose-designed coolants that are vehicle and manufacturer specific. Coolant is a mixture of chemicals such as ethylene and propylene glycol and distilled or deionised water. Glycol keeps the freezing point low and the boiling point high. Inhibitors are used to prevent corrosion, erosion and reduce the foaming of coolant. Coolant is available as a concentrate, as it must be diluted with water up to a ratio of 1:1, or it can be supplied as a premix when no additional water is required. Mixing different types of coolant can have different outcomes. Some corrosion inhibitors might lose their effectiveness when mixed with other types of antifreeze, which may lead to engine failure. Another way to widen the operating temperature range of the engine is to raise the boiling point of the coolant. This can be done with a radiator cap. Increasing the pressure of the cooling system will raise the coolant's boiling point. For every 10 kPa of pressure increase over atmospheric, which is about 103 kPa at sea level, the coolant's boiling point will be raised by 2 degrees Celsius. A radiator cap stamped 90 kPa will raise the pressure within the cooling system to around 190 kPa at sea level, which will in effect increase the coolant's boiling point by 18 degrees Celsius. If the engine heats up and temperature increases, the coolant will expand. Because the cap is effectively sealing the system pressure also rises. The radiator cap will act as a safety device when a predetermined pressure has been reached. When the system pressure is greater than the force of the mainspring, the control seal is lifted from its seat. Coolant exits via an overflow port and is pushed to the expansion tank. As the coolant pressure drops, the mainspring pushes the relief valve closed, and the system is able to build pressure once more. If the engine was switched off at this point and allowed to cool, the coolant within the sealed system will contract. This contraction causes a pressure drop at the base of the radiator cap. A vacuum valve built into the cap is pulled from its seat by this low pressure. A pathway opens up to the reservoir and coolant is drawn back into the system until the pressure reaches a balance with atmospheric levels. At this point, the valve will close. Removing a radiator cap from a hot engine is extremely dangerous. As the coolant exits the system, it loses pressure and converts to steam. Its temperature remains high and will cause extensive burns to any exposed areas of skin. Ideally, a system should be left to cool. A thermostat is essentially a temperature-controlled flow valve. It may be located in the engine coolant outlet or the water pump inlet. Its role is to regulate the flow of coolant to the radiator. The thermostat sits in a housing submerged in coolant. When the engine is cold and the thermostat is closed, a small amount of coolant is able to bypass the thermostat valve and return to the engine. This prevents hot spots occurring while minimising the engine warm-up time. It's imperative that the engine warms up quickly to reduce cold start emissions and prevent sludging of the crankcase. The mechanics of a thermostat is very simple. A heat-sensitive wax and metal pellet is positioned inside a heat-conducting copper vessel. This vessel makes up the main valve of the thermostat. The valve assembly is supported by a frame and kept in the closed position by a return spring. As the engine warms up, heat energy from the coolant is transferred to the copper and then the thermostatic pellet. The pellet expands when influenced by the heat energy. This expansion acts against a piston, which then forces the valve to an open position. If the thermostat is fitted with a bypass valve, it will move with the main valve's operation, closing the bypass port. All coolant will now be pushed from the engine to the radiator. Low temperature coolant exiting the radiator will be pushed through the engine, finally reaching the thermostat. This coolant will absorb the heat energy from the thermostatic pellet, causing it to contract, allowing the return spring to close the valve. This cycle of operation is constant in a correctly functioning engine. Manufacturers designate the thermostat's opening temperature to work optimally with the engine design. Electronic thermostats have now been introduced into modern cooling systems and are controlled by the engine control module. Keep a lookout for our training modules on these. Radiators are heat exchange units used to transfer heat energy from the coolant to the surrounding air. Radiators may be designed as a vertical or cross-flow type, but their operation remains the same. Hot coolant exits the thermostat housing and enters the upper radiator tank. The tank may be constructed of brass, copper, aluminium, or in modern vehicles, plastic. The tanks are attached to the core, which is a series of tubes separated by heat dissipation fins. In newer vehicles, the core is constructed from aluminium. As the coolant is pushed from the top tank through the core tubes, heat energy transfers from the coolant to the tube walls, then to the heat dissipation fins. These fins are angled between the core tubes, much like the pleats of an air filter, to increase the surface area available to the moving airstream. The heat energy radiates to the airstream and is carried away by the movement of the vehicle or the cooling fans. The water or coolant pump is used to move the liquid through the water jackets to the radiator, and then from its outlet back to the engine. The pump comprises of a housing, shaft, support bearings, seal and an impeller. They may be belt, chain or camshaft driven, or in newer vehicles, pure electric. The design of the impeller draws coolant to its centre and is forced to the outer edges centrifugally. A mechanical water pump will only operate when the engine is running. Most coolant pumps are cast with an atmospheric or weep hole that allows any coolant leaking past the seal to drain off before damaging the support bearings. Engine blocks and cylinder heads are cast with galleries or jackets. These galleries ensure coolant is circulated around the cylinder and combustion chambers. Fitted to the engine block and cylinder head are Welch plugs. These plugs are first used to seal the block when the casting sand is removed. The main purpose of Welch plugs is to act as sacrificial anodes. Since the plug is constructed from a combination of zinc and copper, they will corrode before the main engine components. Originally, engine fans were simply attached to a pulley and driven by a fan belt. They had fixed blades and were efficient for early engines. Modern engines require more sophisticated systems. These systems may include variable pitch fans, viscous couplings, or electric fans. Variable pitch fan blades change angle at different engine speeds. They tend to flatten out at higher RPMs, as the higher vehicle speed should be sufficient to supply a steady stream of air through the radiator. Newer fans are constructed of plastic and are designed with the blades asymmetrically placed around the circumference. This reduces blade noise at low vehicle speed. Viscous or fluid couplings rely on engine temperature to operate. At lower temperatures, the fan drive is in a run-free state, so as the engine temperature rises, air passing through the radiator takes on heat. The now hot air influences a thermostatic clock spring found in the fan drive. The spring expands with heat and operates a valve to control a contained fluid flow within the hub. The silicon or viscous fluid is able to change its viscosity with heat and is channeled in such a way that it provides a coupling of the fan hub to form a semi-locked drive. As the vehicle speed rises, the airflow through the radiator is cooler. This has the opposite effect on the control valve and viscous fluid, so the hub is able to free spin. Electric fans are often fitted in single or paired units. These are common in transverse engine configurations and vehicles with larger AC systems. These systems may be ECM controlled. All fans are fitted with a shield or cowl. These are there to direct airflow through the radiator. Cowls should never be discarded or modified. Cooling system hoses are made of a layered and reinforced rubber-based material and are used to deliver coolant through the system. The hoses must be strong enough to contain the system pressure and withstand a very wide temperature range. Some hoses may be found with internal springs that prevent the hose from collapsing when under low to negative pressure. Remember, heat and pressure can be a dangerous combination, so when working around cooling systems, safety must come first. As always, keep training. Thanks for watching.